Okay, now let's consider the two independent samples design. So again, this is a kind of either observational multiple sample design, but where you have two different groups, two independent samples of data that you've collected, or you may be conducting something like a parallel samples experimental design, such as the typical randomized controlled trial, where you have two different interventions or two different experimental conditions that you're comparing. So let's open up our data. We'll open up the independent samples t-test or independent t-test data set from the examples. And what we have is two columns of data. We have gender and we have the amount of weight loss that has occurred as a result of some sort of intervention or perhaps over time. So this is just a change in weight that's occurred. So we have males and we also have females. Now, if you recall from the lecture, essentially what we have here is a categorical or a nominal variable that we want to use to try and predict our response variable, our dependent variable of weight loss. So our categorical variable is our x variable and our y variable is our weight loss. Now this is a case where what we have to do is use something called dummy coding. Now Jasp does this automatically, and what it tends to do is when most statistical software, when you code a categorical or nominal variable using some sort of string of characters, so for example males or females, it will do it in alphabetical order. So it will set, with dummy coding, the value for females, because F comes before before M, as 0, and males will be set as 1. Now you can encode this explicitly if you want 1 to be 0 and 1 to be 1. If you want 1 to be the reference value or the intercept and 1 to be the slope, then you can change these around yourself. Now for the moment, let's leave it as it is, and we're going to go to regression again and go to linear regression. So the dependent variable, the y that we're interested in, is weight loss, and we have a predictor value of gender. Now this one is going to, because it's a nominal, go into the factors column. So we're going to pop that into factors here. And now we get an update to our linear regression output as we do before. Because we've got a categorical variable, we don't get a standardized coefficient here. But what we do get is we get our initial intercept only model, which is our null model, which essentially is just the mean for weight loss across both groups. But the regression model, or the linear model that we've set up here, we have an intercept value, and that intercept value is the same as the mean for the females. And then the slope for gender essentially tells us what the difference between that male group and that female group actually is. Okay, so essentially this is telling us the difference between the groups. The slope for that predictor, that gender predictor, is telling us the difference between males and females. So what it's saying is males are 3.209 less in terms of the weight loss that's occurred, or weight change that's occurred, weight loss that's occurred than males. Okay, now let's go to conduct what is called an independent t-test, which is our typical kind of test that we would use for this kind of analysis. So if we go to t-test and go to independent samples t-test, now we can do the same. Let's add our dependent variable, weight loss, and let's add gender into our grouping variable. Now what you see is that the weight loss t-statistic, although the signs are different just because of the way it codes things, you'll see that they are the same, 6.16, 6.16. Now let's go in and add our descriptives so we can see how this looks. As you can see, the intercept value is 6.929 in our regression model. That is the same as the mean value for the females, as I said. And the males are considerably lower. In fact, what they are is 3.209 lower. If we add the location parameter to our t-test, we'll see that the mean difference that we get is the same as that slope value. So again, you can see this equivalence between the two models. Using that dummy coding, essentially, if we remember rightly, our slope parameter tells us for a 1 unit increase in our predictor, which in this case, if we've got females coded as 0 and males coded as 1, a 1 unit increase means essentially the shift from females to males means that we have a change in our weight loss of minus 3.209. And as you can see, males have less weight loss than the females have. So this is the equivalence between the interdependent samples t-test and essentially a linear regression where we have a nominal or categorical predictor and we use that dummy coding. Again, we have obviously non-parametric versions of these if we use the Mann-Whitney U. So if we were using the rank transformed Y value, then we would have equivalence with the Mann-Whitney U test between our regression and our independent samples t-test. If we wanted to present this data, again, I would recommend using something like the rain cloud plot. So we can have our two variables set aside like this, and we can see how they visually look when we compare the two to one another, and we can use our t-test to actually determine whether there is a significant difference between the two. That is, whether, at least in the case of our frequentist analysis, we can reject the null hypothesis that there is no difference between the two groups. Okay, hopefully again this helps express that equivalence between the two, and that the independent samples t-test is just a special case of our general linear model.